This is day 3 of chapter 14, Reflections. Alright, today we'll be looking at lenses, concave and convex. Alright, first we'll start with a warm-up. Why is the person taking the picture upside down? So if you look closely, in here you have a mirror and the image, there's their head, there's their body, they're upside down. The answer for that? Well, they are probably too far behind. If you're behind the focal length, then your image is upside down, it's inverted. But if you're closer than the focal length, then your image will be right side up and magnified. If you're right on the focal length, you get no image, it'll just be a blur. Alright, so that's our warm-up. Let's move on to today's lesson, our objective. Students will be able to differentiate between convex and concave lenses and do all the calculations that go with them. Alright, so concave and convex lenses. A lens is a transparent material that is able to focus light. That's a lens. Alright, but we got two types, convex and concave. A convex lens is thicker at the center, but a concave is thinner at the center. So that's the difference between one and the other. Also, the focal point for them is different. So if the light's coming from this side, the focal point will be on the other side. This is also known as converging. It brings the light together. And the focal length will be positive. Keep that in mind. It will come up later. When it's converging the light, the focal length is positive. This example for a concave lens, notice that the focal length is on the other side. So for this one, it's diverging. Why diverging? Notice that the light's going away, separating, it's diverging. So the focal length is negative, it has a negative value. Here I went ahead and put it up on the board. Focal length for converging is positive. Focal length for diverging is negative. Thin lens formula, I have it here as well as up here. So it says the focal point is found with this equation. The inverse of the focal length is equal to the inverse of the position of the object plus the inverse of the position of the image. Alright, so it's very similar to the formula, identical to the formula from mirrors. Alright, F is focal length, P is distance of the image, and Q is distance of the image, and P is distance of the object. Alright, and if all the units match, then you don't have to worry about putting everything in meters. So for example, if this is centimeters and that's centimeters and that's centimeters, then you're fine. You don't have to worry about, do I have to convert them all to meters? That's fine. They could even be all inches, inches, and inches, and it'll still be fine, as long as they all match. Now the magnification is done by the following. Magnification, it could either be the height of the image divided by the height of the object, and that will give you the magnification, or the negative of the position of the image divided by the position of the object, and that could also be used. So here I have magnification using their position, here using their height. So either one could be used to figure out the magnification. Alright, so, and then we have one more time. I did want to go ahead and spot this. Did you notice how you have P's and Q's? You have DI's and DO's. Sometimes in some textbooks they'll change the distance of the object. Instead of using a P, they'll use a DO. And the distance of the image, instead of using a Q, they'll use a DI. So I left that there on purpose. I also wanted to point out, if you go backwards, if you squint very carefully, you'll notice that's DI and DO. And yeah, that it's used from time to time. Alright, so let's go ahead and solve some problems. Our first problem is sample problem B out of page 500 of your textbook. Says an object is placed 30 centimeters in front of a converging lens and then 12.5 centimeters in front of a diverging lens. Both lenses have a focal length of 10 centimeters. For both cases, find the image distance and the magnification. Alright, so let's go ahead and get to work on this problem. So let's start with the diverging lens, or the converging lens. Converging was first. So let's start with that. Alright, so we want to go ahead and solve for the image distance. So in this case we're solving for Q. So we're going to go ahead and use this formula, and the focal length is 10. That's given to us. Both have a focal length of 10. Alright, and the object is placed 30 meters in front, 30 centimeters in front of the converging lens. So that's the position. And the question is, what is Q? What is the distance of the image? Alright, so that's for the converging. Notice that for converging, I put 10, that's the focal length, and I put it positive. Alright, so let's go ahead and get to work on this problem. First of all, I'm going to go ahead and 1 divided by 10 will give me a decimal of 0.1. And 1 divided by 30 will give me a 0.033. That's the inverse of Q. Alright, so I'm going to move this one over. And that'll turn into a subtraction. So 0.1 subtracted from 0.033 will give me 0.067, a little bit of rounding off there. Alright, I'm going to move this around, so it'll give me this. Q equals the inverse of 0.067. So therefore Q for the first problem is going to be 15 centimeters. Alright, so that is the distance of the image for our first problem for a converging lens. Next, let's go ahead and figure out what is the magnification of this converging lens. The magnification is going to be negative Q, which we just solved for, 15 centimeters, divided by P. P was at 30. So that gives us a negative 0.5, which means two things. Number one, it's smaller than the original because it's less than 1. And number two, the fact that it's a negative magnification means that the object is upside down. It's inverted. Alright, so that takes care of our converging lens. Now, let's take a look at our diverging lens. Alright, so the object is placed 30 centimeters from the converging, but it's placed at 12.5 centimeters from the diverging lens. So I'm going to change this problem. And instead of 30, I'm going to put 12.5. But that's not the only change. They said it was a diverging lens. For diverging, the focal length is negative. So that's a negative 10. Alright, so let's go ahead and solve this problem. So it's going to be 1 divided by negative 10 will give me negative 0.1. 1 divided by 12.5 gives me 0.08. Next, I want to move this 0.08 over on this side, making it negative. I'll put them both together. That gives me a negative 0.18. I'm going to move this around slightly. So move the Q there and the negative 0.18 there. So it gives me this. And finally that is 1 divided by negative 0.18. It will give me a negative 5.56. Alright, so that is my answer. Alright, let's talk a little bit about it. It's negative. What does that mean? It means that an image is a virtual image. Not a real image, it's a virtual image. So it came out negative. Alright, now let's solve for the magnification. Magnification, again, we're going to use this formula. We have the Q, negative 5.56. But notice how the formula already comes with another negative. So I'm going to put negative there. And P, in this case it is 12.5. Okay, and the negative and the negative is going to give us a positive, so our answer it is magnification 0.44. Alright, what does this mean? It is still smaller than the original, but the fact that it's positive means that it is an image that is upright. Alright, so that takes care of our first example. Up next, we're going to go ahead and do problem number 1 at page 501 of your textbook. In this problem, they ask, an object is placed 20 centimeters in front of a converging lens of focal length 10 centimeters. Find the image distance and the magnification plus draw a ray diagram. Alright, so first we're going to go ahead and do the math, and then we'll take care of the ray diagram. Alright, so let's go ahead and get started. In this one, again, the 20 centimeters is your P, that's the object distance from the lens. Alright, and focal length is 10. So let's start with this formula up here. 10, positive or negative, it is converging, so therefore it is positive. 20 centimeters, and they want to know Q, where's the image? Alright, so let's go ahead and get to work. 1 divided by 10 gives me a 0.1. 1 divided by 20 gives me a 0.05. And now we're going to go ahead, there we go, Q. Now we're going to go ahead and move over the 0.05 over here. We're going to go ahead and subtract. So it's going to be 0.1 minus 0.05 equals 1 over Q. Alright, next, subtract here. 0.1 minus 0.05 gives me 0.05 equals 1 over Q. Rearrange it slightly. So our answer is 1 divided by 0.05 gives us 20 centimeters. That is how far our image will be. Next, we're going to go ahead and find the magnification. We're going to use this formula right here for magnification. Magnification is negative Q over P. So negative Q, or Q is 20 divided by P. Our P is also 20, so therefore it is a negative 1. What does it mean? The magnification, it's a 1, means that it's the size of the image is the same size as the original object, but the negative means that it's inverted, so it's pointing downwards. Alright, so that is our answer for number 1. Now let's go ahead and do our ray diagram. Alright, for our ray diagram, we're going to go ahead and use, let's see, got a meter stick, no, it's a yardstick, and we're going to go ahead and use it, but with 20, 40, will it fit? Just barely, but yeah, it'll fit. Maybe. Alright, so let's go ahead and do our ray diagram. In this ray diagram, we're going to go ahead and put where our image will be. Let's see. Alright, so the object is placed at 20 centimeters. So from here, here is 20, and they put it 20 centimeters from the lens. So we're going to draw a straight line, and this line represents the lens. We're going to put a convex lens right there. Alright, and 20 centimeters is that far. So this is where our object will be. That's our P right there. Also worth noting, 10 centimeters, that's a focal length. So right there, I'm going to put an F for that's our focal length. They did not say how big this object is, so I'm just going to make it 4 inches tall. So there we have it. Now we're going to go ahead and draw our ray diagram. We're going to do 3 lines for this ray diagram. Our first line, it's going to go ahead and be from the top of the object to the lens, and then it's going to go down through the focal length on the other side of our lens. The focal length, remember, was at 10 centimeters. So I'm going to go ahead and do another 10 centimeters on this side to get the focal length on the other side. Alright, so let's do that line. From the top of the object to the lens, that's our first part. Oops, sliding on me. There you go. And once it gets to the center, it drops down through the focal length. Alright, so there's our first line, we got that done. Next, our next line is going to go from the top of the object through the focal length, hit the lens. Alright, and then after it hits the lens, it's going to go ahead and parallel this other black line. And where they meet, that is where our object is. Alright, so they meet right there, and that is where our object is. Is that straight? Doesn't look too straight. Let's see. Oh, it is not straight one bit. Is that straight now? There we go, it's a little bit better. Alright, and so there we have it. Line from the top of the object through the focal length, from the top of the object through the focal length and straight back. And where they meet right here. That is where our image is. And notice the image will be upside down. So there's our image. Alright, according to our calculations, the magnification was -1. That means that the image was upside down. It is, and it should be the same size. I made this one 4 inches tall. So you see the 4. And this one is also 4 inches tall. So there you have it. We also said that it would be 20 centimeters from the lens. And there it is, right at 20, where our two lines met. Alright, so there you have it. That is how you would do a Rade diagram for this problem. Now our next one. Oh, it froze on me. There we go. For our next problem, number 2, in this scenario, they ask you, as Sherlock Holmes examines a clue by holding a magnifying glass at an arm's length and 10 centimeters away from the object. The magnification, the glass has a focal length of 15 centimeters. Find the image distance and the magnification, plus draw a Rade diagram. Alright, not sure about that second Rade diagram, but you guys get the idea. It goes from the top of the object into the focal length, and from the focal length all the way across. Well, let's go ahead and do the math for this problem. One more time, the focal length was 15 centimeters, and previously has stated that at 10 centimeters, that is where the object is, so therefore that is P, 10 centimeters. It is less than the focal length. Alright, so that would change our image slightly. Alright, now, next one. They want to know Q, where is this image, and what is its magnification? Alright, so those are the things that they're asking of us. Alright, so let's get to work on Q first. We'll use this top formula right here. So 1 over F, we know the F, and it's a magnifying glass. Those are converging, so therefore it's positive. So 1 over 15 is equal to 1 over 10 plus 1 over Q. Alright, so we're going to begin 1 divided by 15. It's going to go ahead and give us 0.0666. We'll round that off to 0.0667. 1 over 10 gives us 0.10 plus 1 over Q. Now move the 0.1 over to this side. So it becomes a negative 0.1. Alright, so I subtract minus 0.1 gives me a negative value of negative 0.0333. Now I'm going to rearrange this formula, and it ends up giving me this. So our Q is the inverse of 0.0333. It is negative 30. Negative 30. Alright, so that is our image. It's a negative. That means it's a virtual image. Magnification. Let's see. Can we fit it in here? Sure, magnification is negative Q over P. Negative Q, negative and a negative. That's going to give me a positive, and the P is 10. So this one is going to be 3 times its original size. Whatever it is 3 times its original size. Alright, so that is that answers the 2 questions that they had for us. What is the distance of the image? And the answer was it was negative 30. And what is the magnification of the magnifying glass? It makes everything 3 times larger. Alright, we're going to skip the Rade diagram because I'm not sure I have a lot of space here to make something this size. So we'll move on to our last problem for this one. It says an object is placed 20 centimeters in front of a diverging lens of focal length 10 centimeters. Find the image distance and magnification and draw the Rade diagram. Alright, so for the Rade diagrams, I'm going to refer you guys to the book. You can find them page 500 as examples of converging and diverging Rade diagrams. Alright, and in this problem it says the object is placed at 20 centimeters from the lens. And it's a diverging lens, so the focal length is negative 10 centimeters. Alright, and again they want Q. And what is the magnification? Alright, so let's get to work on it. So 1 over F is equal to 1 over P plus 1 over Q. That is a formula for a thin lens formula. Alright, so it's going to be 1 over the inverse of 10 is equal to 1 over 20 plus 1 over Q. Alright, so let's put it into a calculator. 1 over 10 is 0.1, which is negative. That is 0.05. Then we're going to go ahead and move this one over here. That makes it negative. Put them together, it'll give you negative 0.15 is equal to, sorry, that was an equal sign right here. The inverse of Q, so we'd rearrange it. Q is equal to 1 over the inverse of 0.15. So 1 over 0.15 gives us 6.67. That is the distance of the image. Alright, notice it's negative, therefore it's a virtual image. On the other side, magnification. Magnification is going to be Q over P. Q is negative. The formula already has a negative. Negative and a negative will give me a positive, so it's going to be a positive 6.67 divided by P. P is 20. So that gives us an image that is 0.33 in magnification. 2 things about it. It is less than 1, so therefore it is a smaller image than you would expect. And it's positive, that means that it is upright. Alright, so that takes care of sample problem number 3. And again, for the Rade diagrams, I'm going to go ahead and refer you guys to the book, page 500, has those. Alright, let's wrap up this lesson. A little bit of extra practice would help out. So, homework 36, page 515, question number 24 and 64. That's your assignment. Alright, that concludes chapter 14, and good luck with it.